paper, and actually is a joint work with our master students at Politecnico. So we discussed today with Michele that there is a lot of interest in MapReduce and in Hadoop, which is its open source implementation. And actually there are a lot of decisions that must be taken considering such environment. In particular, with Hadoop 1.0, these were the main problem to solve. So we have a set of jobs that can come from different users. We need to decide where, who is the first run, because for example here we have also the first in first out scheduling, which has some limitation. We may need to allocate the jobs to the underlying hardware. We need to understand how many resources within a given machine to allocate to individual jobs and to individual tasks. And there are also some other related issues, that is the monitoring and the failure handling, that can have a feedback on the scheduling and on such decisions. Actually, within the Hadoop 1.0 framework, all of such decisions were taken within the job tracker that could, most of the time, could become a bottleneck itself, and was also a single point of failure. Because of such problems, within the new Hadoop, the new implementation, this problem have been separated and managed by two different system components. So actually, for what concerns the resource management, so the question on who runs, how many resources I should allocate to a given application, such decisions are taken within what is named the resource manager. So here, the resource allocation is like what we do today with VMs, because, for example, here the requests are in terms on how much memory should I allocate to an application, how many cores. So this is the level of granularity of the problem taken. Vice versa, for what concerns the jobs, there is another component, which is the application manager, that actually really take into account the execution order and also monitor the progress of jobs executions. And actually, this is also because the scheduling is application dependent. So one of the new features of Hadoop 2.0 is the fact that the framework allows to define a pluggable scheduler, where so you can take into account the application-specific needs in a way that you can optimize the execution of your application by exploiting such kind of information. Resource manager and application manager are implemented within YARN, which stands for yet another resource negotiator. These slides summarize the evolution of Hadoop from the first release to the current release. And as you can see, the resource management now is split, as I told you, within YARN with these new components. And actually, the new thing is also that while before Hadoop was related, especially was built around MapReduce, now MapReduce is just an application that runs on top of YARN. And actually, what we do have today is we have tags, which allow also, with MapReduce you have first map, then reduce, you have an application that are executed in pipeline, but there is this strict relation among jobs. Well, for example, with tags, you can specify your application in terms of a directed acyclic graph. You can have some kind of optimization also, because you can remove some synchronization barriers. And on top of YARN, you can even really run traditional applications. So in this way, you can have a single system to manage your clusters. So why scheduling is important in such kind of systems? Actually, these slides show the result of the execution of the sort benchmark, where actually here the blue line is, so here today we can mention the concept of slot. So a slot is a share that is allocated for the execution of individual tasks that could be mapped or reduced. And as you can see here, actually we are allocating here 64 slots for the maps, 64 for the reduce. And actually here the red line is the copy shuffle part, which as you can see is a significant execution time is devoted to the data transmission from the map to the reduce jobs. And so here you see that overall this application finishing around 40 seconds. But actually, if we perform a different resource allocation and actually introduce, for example, here we are devoting 16 slots to the map, and in this case you see the map requires 4 different waves, so 4 different iterations, and of course this delays a lot, also the reduce, because you know, the reduce cannot start until the last map has finished providing its results. So the point here is very difficult to predict jobs execution time. You need to know to understand the dependencies among the tasks. So this is why the scheduling is a difficult problem, and this shows how this impact also on the overall application performance. If we consider a scheduling policy, a scheduling in general, the scheduling goal try to solve one or more of these issues. So we were mentioning today the data locality problem. The data locality in city slots are 2 related problems that are related to the fact that if the data is not available to a given task, data need to be transmitted over the network. So data locality try to allocate the task within, to close to the data they need to consume. While the sticky slots is related to the fact that some tasks can even be reallocated because of this. The skewness is another specific problem of map reduce. As I told you, a reduce cannot start before the map has finished, and in that case, so a very slow map could have a huge impact in the overall application performance. So this is the skewness problem. This actually happens also, for example, in data streams systems. While the other things, the system utilization, starvation, fairness, you know, MapReduce actually is a very scalable paradigm. Nowadays there are systems at Hadoop that even run on 35,000 nodes, physical nodes. So scalability is easy, but at the very end, the utilization, the system utilization sometimes is low. Then the starvation is related to the fact that some tasks can be delayed, and of course this is an issue. You never get your resources. And finally, the fairness is related to the fact that you would like to differentiate the resources and the quality of service to different applications. So if you really look in the literature, we can classify the optimization approaches in 2 layers. One that focus on the problem of optimization at the application level. So actually here you have the overall goal is to optimize query like pig and I, so you are at the top of the application stack. While the task scheduling, you focus on the scheduling of tasks. So what you want to do is you want to improve the first in first out scheduling of standard scheduler of Hadoop 1.0. If you look at the problem at the application level, actually there are 2 main families of work. A lot of work has been done by HP Labs, and there are a lot of work started in the paper by researcher Krasova. And actually, these two frameworks are ARIA and AutoTune. There are some slightly differences. And the other totally different approach is what is reported here is as a signature-based, and actually is by this Kambatla and other people. So actually, if we want to characterize the approaches at that layer, we have actually three main steps. The first step is job profiling. What we would like to understand is actually how much are the resources that are consumed by your application, and you would like to characterize this as a function of the input data. And the second step, performance modeling, would given a configuration and given the actual size of the input data, you would like to estimate the job's workflow execution time, while finally at the optimization and scaling step, you really would like to allocate the optimal number of MICAS and user slots in a way that you are minimizing the resource usage, but you want to also usually guarantee some execution time deadlines. So if we look at the job profiling, actually the two, both framework, the signature-based and HP Labs work, try to exploit the data of the previous run. In the previous case, so for ARIA and AutoTune, what you want to understand is which are some bounds, upper, lower, and average execution time of such jobs. While vice versa in the signature base, what you would like to get is the signature of the resource usage of your application. In ARIA and AutoTune, actually, the focus is on the execution. While the signature based focus on always on a small fraction of input data. So you have your own application. In this profiling, you just focus on some micro data, not real data. In ARIA and AutoTune, you do the two both things. You consider really the previous run, and you consider also smaller inputs on smaller clusters. Then in the performance modeling, you try. So ARIA and AutoTune try to summarize the data from the previous run in a way that you can predict the execution time in terms of CPU and maybe network. Another important thing is the selectivity level, both the method and the user. So you would like to understand how, for example, if you start from 1 terabyte of data, you would like to understand which is the size of the data that you get as a final result of an initial processing, because in general you have a really complex directed acyclic graph in your application. While vice versa, what you do in the signature-based approach, you compute actually the distance between a set of applications that you have previously optimized with the new and current application. And finally, the optimization step, actually ARIA and AutoTune focus on exploiting the Lagrangian multiplier method as Michele has shown today. Actually, we have extended the work of Cherkasova. And because of this, you can get, by closed formula, which are the number of maps and reduce that you need in a way you can satisfy some deadline. Within AutoTune, the authors did an initial step, so they were able to identify also some Pareto fronts that allow you to understand how vary the system performance according to but that are equivalent with different maps and reduce in a way that you can take some more informed decision during cluster configuration. Vice versa, in the signature-based approach, the optimization step is very easy, because actually the rationale here is I know in my system